Okay, so today is going to be more about data analysis and how we can obtain specific information about different deformation mechanism in specific. So I will just quickly go that what we do. So I will be talking a lot about. Can everyone hear me properly, right? Okay. Cool. Okay. So I will be talking a lot about time of flight, and as you may already know that time of flight. So neutron beams, so they are of varying wavelength, which emerge from the source, and then they interact with the sample, and then they diffract towards the detector. And basically, it follows the same Bragg's law, which we use for X-ray diffraction, for example. But in this case, there is an additional thing, which is time of flight, which is the time it takes from source, neutron, take that time from source to the detector. And so we can modify this Bragg's law by using momentum. And this is times constant, and these velocity and mass of neutron. And this is just, we can change it to relationship this one. And ultimately, if we substitute lambda for this, then we can obtain this equation, right? So B H by 2 ml sin theta into T. And all of these are constant in case of these instruments. And you can see lattice spacing G, right? And H is times constant, M is mass of neutron, and L is source to detector distance. And the theta is that angle. And as I mentioned yesterday, for most of these setups, the theta is usually 45 degrees. So it is fixed for specific instrument. But of course, depending on which kind of experiments you are doing, it can vary. But they will give you value for that. And ultimately, they will provide a constant factor for this in black, so that you can just multiply it with the T, and you can get this spacing. That's what we're after. That's how we obtain structure, right? So T is time of flight. Okay. You mentioned, you remember how neutron scattering happened. Yeah, it's very funny figure. I really love it. It is made by someone else, I think, a long time ago. So the principle is neutrons, when they're coming from a beam, a source, they are polarized, so they have to be directed towards the sample. So once they go there, so then they will interact with the material, they will interact with the sample, and then they will be diffracted, and we get them in the counter. Right. So how the main thing, because I work with the deformation behavior, so I will be mainly talking about that, but the principle applied to other methods in a similar way. So when we want to study mechanical behavior, institute mechanical behavior, so what happens? So we have a polycrystal, right? And there are grains which are oriented along different orientations. And when we apply a beam, we X-ray, neutron, whatever it is, so we get lattice spacing. So we get a diffraction peak and at a specific lattice spacing, right? So when we apply stress, that's what we do. We are pulling our sample under tensile loading. So what will happen? The lattice will stretch, right? So when that will happen, then basically the peak will move. That's the one thing. But if it's just peak shift, then it means usually just elastic deformation. And basically from peak position, we can obtain lattice strain and stacking fall probability. Then also peak can broaden because of subgrain structure, for example. And then you can also see its intensity can change as a result of stress, and which is because of texture during deformation. And we can obtain information about texture, and twinning have different kind of texture evolution compared to sleep. I have shown some example yesterday, and I will, probably there will be some more. Okay, so this is the main, underlying principle that everything which we obtain about mechanical behavior, characteristic that is coming from these peaks, these and changes in these peaks. So, which will be relative to the initial state. So this we can say stress-free, and then this is under stress. Am I very clear? There is like kind of vibration. Is it okay? Okay, so now the focus of today's 1 hour talk will be about processing of time-of-flight data. And as I mentioned, that we get time-of-flight data and we then just convert it to respacing, backline, factor. So what we do basically it refinement. Whether you have simple structure or it is after deformation. So you do it will refinement by. So usually we use this software called Zero. Is freely available because this software is produced by Japanese researchers, specifically who are working at Japan Photonics Research Complex, and mainly they use it for their data analysis. So they have all the factors inside this package, and they also have online manual for that, so you can freely download it. And there is also instruction if you want to make your own. You need a histogram file, which is raw data, and then you also will need a factometer file, which is instrument file, because instrument will have their own kind of factor. So you can also make that by following this manual. So you can just Google Zero software and you can have the whole package. They have very clear instructions, very easy to follow. And the advantage is that you can use it for multiple features, which is very helpful, because when you get institute data, that can be really huge sometimes. And it have like a lot of diffraction patterns, so it is very difficult to process them one by one. So they also have batch processing which you can follow. I would highly recommend to check out this package. And they, by the way, they also have sample data for different kind of materials, including alloys, so that you can try and see how it works. So that can be very, very good for learning purposes. And they have a very simple manual to follow as well. And then if we have to obtain, so after fitting data, we can obtain, how we can obtain orientation dependent lattice strain. You remember yesterday I mentioned that what is lattice strain and how different family of grains behave in a different way because there are intergranular stresses among them. So we denote strain with epsilon, and HK mean they are for individual lattice planes, 111 for example. And what we do, so basically directly we can also do that, which is T of is time of flight for individual reflection minus the reference one. Reference one should be before deformation or stress free, depending on what you really want to. For example, if you want to do you want to make residual stresses, then you have to get a stress free sample, which means it should not have any stresses at all. But if you are doing deformation, then you are looking at relative. So that should be just before a deformation started. So that will be the reference one, and you can, this is simple equation. Or you can also use the spacing after fitting in this data. Right. So this you do for each peak, and you can obtain their behavior. And I mentioned that because of elastic anisotropy, so they have initial scatter during the elastic region, and then there will be elastic anisotropy, and then we have further split, and they will have 200, for example, is a very compliant plane, while on the other hand 111 is stiff. And the texture estimation, again, like we have to compare it with the initial one or the stress-free one, so we can see how the texture is changing. Usually we get a different kind of texture when we look through, for example, usually people do it by EBST imaging, but here you can get from intensity change. This I'm specifically talking about this engineering materials diffractometer, but some facilities all have a different kind of instruments where you can get the pole figures directly as well. Because for pole figure you have to scan at different angles. In this case you have just 2 detector banks, so you cannot really construct pole figure in that way, but you can have estimation about different kind of intensity changes, and you can deduce from that, like, okay, texture is changing. Would it be because of distribution slip, or is it because of some other mechanism? Okay, So I also mentioned about stacking fault probability, which we usually obtain from, in this case, from lattice strain. And we follow a very old method which was proposed by Warren in 1950s. He had 2-3 papers on that. And now it is in his book, this axial diffraction book, which I think they use a textbook in most of undergrad courses. So there is this equation which he proposed to determine a stacking fault probability. And you can see this is from this book. You can find it and you can read details about it. It has some limitations. Of course, everything has some limitations, how much you can apply to it. So, but this uses, you can see 2 theta, difference in 2 theta over here. I can just go through, like, these are different factors. So this is peak displacement, because how much peak have moved compared to the reference one or the stress-free one. So that would be the change in that. Then this is alpha is a stacking fault probability. That's what he used in equation. And of course, this is angle, and this h0 square. This is what is for. So I'm talking here specifically for cubic system, and specifically for phase center cubic in this case, because in FCC we expect mostly stacking faults. Stacking faults, as I mentioned yesterday, they are faulty planes within FCC system. So if you remove, so we have stacking of ABC. So if you remove one plane out of that, then you will have intrinsic stacking fault, which means one plane is missing. And if you add an extra, like there is an extra layer of atoms, then that will be extrinsic stacking fault. And similarly, there is twin fault, which is mirror image of those planes. So in this case, so basically, intrinsic stacking fault is also considered as HCP structure, because that's how HCP is stacked, AP layers, right? So if it is irregular occurrence of those faults, then they are stacking faults. But if they combine together, then they convert to HCP. Anyhow, that was a bit of it. And then these are some parameters which can be broadened and unbroadened during the deformation. Okay. And basically, we can simplify this equation. We can convert this equation to lattice strain. So here it was displacement in angle, but usually for us, angle is fixed. So we have lattice strain. So from that, we can deduce. So remaining, everything remains same, but some factor we just can change to epsilon HKL. You can actually try to derive it. It is very simple. And in the book, you can also find this table, Warren's book for XRD. You can also find these constant factors for different planes, different reflections. So you can substitute them, and you can obtain at the end this equation, which is very simple. And this is what we use for stacking fault probability calculation. And you remember, as I shown yesterday, that if there is no stacking fault, then these two reflections, they should have the same behavior, because they are parallel planes. So 1, 1, 1, 2, 2 should have the same behavior. But when there are stacking faults, then there will be difference between them, and with deformation, this difference increases, then it means stacking fault are increasing. And this is very, very simple method that we usually apply from diffraction data we have in situ data. Of course, you cannot use it if you have only one data point, and then you say, okay, I want to get stacking fault probability. I think that is not advisable, because it may not be really, you can have an error in that. But if you have large data points, like 2 at each point, then you can really say, okay, this is real, this is really a trend which you can follow. Okay, this was about lattice strain and then stacking fault probability. Now I will go a bit about one method which is known as convolution multiple hole profile analysis, which is basically because our peaks are convoluted, right? And they have contributions from different kind of factors. Okay, so our profile can have contribution from our course instrument itself, the intensity which we obtain. Then it will be because of strain, and then there will be contribution from planar faults. So it is a convolution of a number of parameters. And not just that, within, for example, for dislocations, you can have different kind of dislocation character. For example, it can be edge dislocation, screw dislocation, Then similarly for size, you have median, variance, and so on. So it is convoluted. So this package was actually, the main work was done by Professor Tomas Shunga and his students. Mainly one student who really wrote thesis on that. And it is also, his thesis are also available, and this package is also available freely on, and they also have some instructions for that, and also some sample data which you can try. It is a bit complicated, but you have to try and see how it works. You can try with simple material which have maybe just dislocations, and then you can see how that works. But when it have other defects, then it becomes more complicated. Okay, so basically, the peaks which we obtain, they can be, they have these kind of contributions. So it's convoluted. So the main thing which we want to do is to deconvolute. So we can see which contribution is, or how much contribution is coming from which mechanism or which parameter. So within size, as I was mentioning, so for size parameters, so they define, so when you will look at that package, I did not put, I should have put one screenshot to show like how that package look like. Maybe in the future. So it have number of parameters which you have to solve simultaneously. So size parameters, there can be two things. One is median, and the second one is variance. And how basically you are trying to get average crystalline size, right? And basically these two factors will determine what is the average mean crystalline size. So this is basically the factor, and you will have these two parameters within that package. Then the other one are dislocation parameters, or strain parameter, which is over here. So you can have a dislocation character, as I was mentioning. So you can have, maybe your material have edge dislocations or screw dislocations, or maybe mixed of those. And then of course dislocation density itself, and then also effective outer cutoff radius for dislocation, because they have a certain length. And also one thing which is in addition to these is dislocation arrangement. How dislocation are arranged, are they coordinated or disoriented? So that is another parameter. So this becomes very complicated, and if you don't have good quality patterns, then it becomes difficult to solve them, because the error becomes higher. So that's why we sometimes determine, we spend longer time to measure a pattern, or we give a longer time. And also we do usually slow deformation mode, like deforming material very, very slowly, so that we can accommodate statistics, so that we can have a good pattern and we can fit it more accurately. Okay, so to deconvolute distribution part, because that's the one which we are most interested in, we want to know distribution density. Because with any other method, it's not easy. For example, with the TEM, as you know, that we just look at really, really tiny areas, maybe micron size. And in that, if you want to look at dislocation, you have to really count them, how many dislocation you have. And when dislocation density become high, you cannot really do that. You cannot really count them. And sometimes dislocation density can be like as high as 10 power 15 or 10 power 16 per meter square, which is very, very high dislocation density. So it is not possible. And also that is kind of not a full representation of the sample. Usually we have structural materials, we have very large sample. So we have to like kind of look at bigger picture. So again, I have to mention that this is not like perfect, but this is the best which you can get. Okay, so now we can focus on dislocation density, because dislocations are the one which really determine all of the properties. I mean, we have planar force, wave transformation, but still the main deformation mechanism is dislocation slip, and they determine like how strong our material is, how ductile they are, and they are the main thing. So we have to know about their density. There was a few years back, there was a paper which was published in Science about steels, which was partition steels, and they estimated discriminant density up to 10^16, and they said it's the only thing like which is making this a lot. So its yield strength was almost 1700 plus megapascal, plus it had really good ductility, 15%, so which is very high, and was for steel. So, and they claim it was just discriminant density, which is the reason for that. Okay, so in this equation, you can see there are a number of factors. Basically, this is as you can see from the previous one. So I am talking about this part. So size is covered over here and the strain part. Instrument is like we have a background file for that. Right. So basically, there are three things in this equation which you can see. One is diffraction vector, and this one over here, which is related to wavelength and theta. But here we directly get the spacing, so it is just 1 by g. We also called K, at least in our community. Then there is mean square strain, and third I forgot. I think it's the distribution length. And the mean square strain is then consists of a number of factors, and that's where distribution density comes in. So distribution density, this is a contrast factor. Then we have Burgers vector. Burgers vector, for if you have crystal structure, then you know how Burgers vector is calculated. And Wilkins function, because they built on Wilkins model, the Martian rise and this team. And Fourier length, sorry, this was Fourier length. And this is outer effective cutoff radius. And then we can now, so it is kind of like solving number of parameters, and then within those parameters we have further parameters. And but when you use that program, so you have to understand these basics, so that you can really know if it is correct or not. Otherwise, of course, you can get, it is somehow like how we know, like GIGO, right? Garbage in, garbage out. So you can, like, of course, you can input something and you can get something out of that. But if you don't know like how it works, or like if it is really correct, then of course it will be useless. Right. So contrast factor is related to type of distribution. And we usually use every contrast factor, which is we use, for example, for phase and cubic system, we use 200 diffraction, and they have a software for that as well to calculate that. So you just input single crystal, what is called diffraction, elastic constants C11, C12, and C44. This is, of course, I am exclusively talking about cubic system here. For HCP, you will have a different kind of arrangement. So you just put in these things, and you can get every contrast factor. And this is distribution character, as I mentioned, that you can have edge distributions, full distributions, or they can be mixed of those two. And this is H square, which we also call gamma parameter. And this is again for cubic. This is how it looks like. So this is for dual reflections. And then you remember I mentioned about distribution arrangement. That is actually related to effective outer cutoff radius of distribution and distribution density, square root of distribution density. So if it is depending on like how small or how large its value is, then you can know like the distributions are very like arranged in particular way, or they are like just randomly arranged. In this I just showing you just from my own results that I wish actually I had a plan when we discussed about this course. I had a plan that I can maybe show, I can run software over here and I can show that how it is done. But then I realized it would take a lot of time. It would be really, because there is so many things inside that. So I could not do that because you need more time for that, and this is very, very short time. So I was like, okay, I can just show that, and I can put some dots that how it would look like. And if you are interested, of course, I can, as I mentioned, that it's available on the web. You can just look it up, and it have a simple instruction, but sometimes it becomes hard to follow. So in case if you have any questions or if you want any help, then of course, please feel free to contact me. Okay, so this is, you can see this is during deformation, and this I'm showing for one of the high entropy alloy at low temperature. So for that, we saw that, okay, this is in the beginning, it had, so sorry, I don't know why this is not appearing over here. This is basically line for pure edge distribution, and this is for screw distribution. And people, I mean, from the very first study with neutron diffraction, they concluded that distribution but you can see that it's mainly during deformation is mainly around that level. It's like both edge screw distribution mixed. So this parameter, when you are solving this, you are solving a pattern, you can get this information. Then, as I mentioned about effective outer part of radius, and this is a dislocation arrangement. So how that parameter changes, almost not much change, to be honest. And then similarly, size parameter. So when we do deformation, grain size become, because deformation, crystallite size become, I would say, smaller. So that's what we're talking about. So you can see this is how the size, what is it? Anyway, so it goes down, while this almost then after is not much change. Sorry, this is those two parameters, m and sigma, which is variance and the median and variance. And this is basically the crystallite size. So it starts from here. This was the crystal size in the beginning, and then it goes down, and after some time, you cannot refine less than that. So it becomes very, very actually small like that. Okay. Alright. So you can obtain, so this is, I'm showing the CMWP fitted patterns, the package which we use, and at the end we can, after using all of these parameters, and so the one thing you have to have, of course, it have to fit well. And this was mainly dislocation density. And I have shown for two strain levels. So one is almost in the intermediate, and the other one is at the end of deformation. And this is phase center cubic structure, right? So you can see, and also we know from RWP factor, we use different kind of parameters to know that if the fitting is good or not. So for example, GOF we use good of fit, or we also use the weightage residual thing. So there are number of factors. So if it is less than 10%, usually we consider it to be a good fit. So of course we can, of course how small it is, that is good, but there is a limit up to what extent you can go. So this had, so I'm just showing you that this was black points are Neutron diffraction data points, and the red one is fitted by this software, and the blue one over here is the difference between these two. And just I'm showing like after this, you can obtain this kind of information, and you will have distribution density, which is what we are after. But you also have to take into account other parameters. Okay, this is just I'm showing this whole for this high entropy low temperature at different data points, distribution density value. And for this one, we had lattice, 3D deformation, and there was, we thought that this is because of, this drop is because of that. Okay. Okay, how much? Okay, so, as I said that I had planned to talk about how to run this software, but I think that will be like a lot of work. So I did not do that. So basically my purpose was to introduce that how you can use these packages, and you can get information from online. And if you have any questions or any difficulty, of course you can, I think Professor Gonzalez is here, maybe I think he also worked with these kind of packages. But feel free to contact me as well if you have any questions. Now I think I can talk a little bit about, as I mentioned yesterday, that someone asked question that how much it costs to conduct these kind of experiments, and if you want to get neutron beam, how to obtain that. So maybe I can talk a little bit about that, and maybe 10 minutes or so. So basically the answer which I gave yesterday, actually it is free for anyone to obtain neutron beam time at any facility. And there are a number of facilities around the world, in US, in UK, France, Japan, China, Germany, and so on. But you have to do, so if you are doing research and you are intending to publish that, it is for student thesis, then you don't have to pay anything at all. But you have to compete with other people who also want to do, because it's very, very, there are very few facilities around the world, and it's very, very expensive. And if you want to use it for commercial purpose, I know the cost for the one facility in Japan. So they charge 3 million yen. I don't know how much is 3 million yen in pesos. So they charge 3 million yen per day of beam time. So it's very expensive. if you want. So a lot of industries, especially automobile industry or aircraft industry and steel industry, they really get beam time and they pay for that because they don't want to disclose their findings. But for student theses or for research which you want to publish and want to make public, for that it's free of cost. But for that you have to write a proposal, like how you write proposals for funding or proposals, or maybe like how you write paper for publication, kind of mix of both too. So in that proposal you have to take into consideration number of factors. First of all, of course, the thing which you are trying to investigate, it should be new, like there is some really fundamental or scientific issue which need to be addressed. It's something new. I mean, if it's already done by other people and you just want to read to see how it happened, then I think it will be just wastage of very expensive resources. So this is the first factor. First thing, that it must be worth exploring. It must address some technical scientific issues. Second point is that you cannot do it by other means. So you also have to say why is neutrons a necessity to carry out that kind of work. So if you can satisfy that, then you have to write a proposal. So I mean, first of all, you have to satisfy yourself, and if it is good enough, of course, you can submit, and then they send it for peer review. So the expert in that field, they review your proposal, like how the funding proposal are reviewed or how our papers are reviewed. So after review, but in this case, after you get review comments, you will not be able to respond to them, as far as I know. So I mean, if those referees think that's good enough, and then they have their own technical committee for each facility, as well as they have their international advisory committee. So then they will have their review, and then they will make decision that because how much days the facility will be running. It's not that it does not run 365 days. So usually they run 2 cycles. So they call for proposal twice a year. Usually, for example, Japan, because I'm more familiar with that, I have been doing experiments over there for the last 7 years almost. And they have calls twice a year. Once in May, so the deadline is second week of May. And the second one is in November. So usually the deadline is around mid of November. Similarly, all the other facilities also do the similar kind of thing. But still, it does not function like a whole year. So it's like usually 6 months they have to shut it down for maintenance, refurbishment, like in parts. So they have limited, and also depend like how much funding they have to operate it from government, because all of these facilities, they are run by government. For example, in US, Neutron facilities are basically run by Department of Energy, DOE. Similarly, in Japan, it is run by Japan Atomic Energy Agency. So some kind of government body decide. I mean, government body have to get funding, and then they have to distribute funding between different kind of facilities. So when you send your proposal and it is reviewed, and if you get positive comments, then again, like you have to complete like how many people are better than you, or whose proposals got better comments. But depending on like if you really think like it's something new, I think it's worth trying. And also some facilities have a new scheme, at least for Japan I know. They have some program called new, I mean the people who are not already in neutron diffraction and they want to get into the community, for that they really encourage them. So they give them big preference. They have a special kind of, like you can say, days for them. So in that way you will get the benefit if you already are not in the community, so that they want to expand the community. So I can just show you, like you have to of course fill like technical information, but I can just show you. Let me see. I can share my own proposal which I wrote a few years ago. I think because now we already have published that, so I think that should be okay. Okay. So let me see. How can I?
We will say a word.
Sorry.
We will say a word.
Okay, that's good. Good to know. Okay, I have to see that how I have PDF. I don't know, maybe if anyone can help me, then it would be great. Does anyone know how to do? Yeah, sure.
I'm not gonna lie, I'm more on Windows user. So maybe it's.
Yeah, because it does say over here, slideshow, but the issue is I don't have
Can we minimize this?
Yeah, so you can minimize from here, yeah. And
that was not the word. Then
no, it's not.
Make the window smaller.
Okay.
Not on the.
Okay. So basically, this one will
No.
So you want me to make a small?
Yeah.
So these are basically some of them should work, but it doesn't. Thank you for screen. How about this?
How are you doing this lecture?
Oh no, that was from PPT. For that, you just do this. I don't like what is starting this one. Just. Okay. Okay. I should have Word over here. Let me.
Is it in Safari?
No, this is Word file. PDF. Sorry, PDF.
Not sure, but it does not.
Yeah. This one should do something. Right?
It is not the.
It does not appear. Can you ask maybe because they should change?
Yeah, I don't know. Because Windows doubles the screen.
Yeah.
You can just drag it. Screen, I don't know.
This should depend on this. Okay, then I can just.
Yeah. Sorry. It's not that.
No worries. Okay. Okay, it seemed like I cannot project, so I can just. I cannot show it over here, but maybe I can just share with you some of the points which you have to take into consideration. Okay. So first, you have to define. So they have. By the way, when we write funding proposals, we have to. Usually, it is like a bit longer. But for beam time proposals, usually they are from 2 to 4 pages. So it's really you have to just focus on the beam, like main part, important things. You don't have like the other things. So for example, for Japan, their limit is 4 pages. So everything must be within 4 pages. And sometimes people can make smaller font for fair, for the sake of fair comparison. So they ask to use specific font size as well, so that you cannot squeeze too much into that. If you cannot explain your problem like in a very like condensed way, then it means it is not really good problem. And it means like you are just trying to expand on something. So for UK, their facility is called ISIS, and I mentioned why they call it ISIS. Their proposal is 2 page, limited 2 pages. Similarly, Oak Ridge National SNS facility, they also ask for maximum 2 pages of proposal. So in the beginning, so as a first part, you have to give a background of your research for the proposed experiment, and you have to mention about research trends and status of your research, because you have to tell that okay, this is a hot topic, this is worth investigating, and you have to pinpoint what is the specific question which you want to address, and you have to supplement that with some experiment results. I mean, you cannot just invent a new material and you can say, okay, we'll study a new material and we'll have this, but you don't show anything else. So you have to include some evidence, for example, from other methods, say TEM or maybe XRD or maybe some other method which you can use. So this is the first thing. So this is kind of, you can say, background literature review plus burning question. And then you have to, the second part is about the purpose of proposed experiment. And if they ask you to clearly state intent to clarify in this experiment and referring to a summary of previous work, including the preliminary experiment. So you have to show some previous results, and you have to show that, okay, this is one point which we cannot do by other methods, and we want to clarify by using Neutron, say, diffraction. There are different kind of Neutron scattering techniques, but I'm just saying that. And then you also have to, so you give these kind of information, then you have to mention that if you are familiar with the experimental method as well as data analysis method, okay, you can go, you can perform experiments. They have dedicated people over there which will help you to do experiments. They will also give you a bit of introduction. But if you don't know what to do with that data, you don't know how to analyze that data, at least you should have an idea about that. Then it is not worth, because you will have data, but what you will do with that? If it is not worth publishing, it is not really worth answering the question, then so you should have a clear idea about that. Then you have to justify how much time you want to request, and you have to really, I mean, in terms of like minutes actually. So you have to say, okay, I will heat sample from this temperature to this temperature in this kind of steps, and then I will do loading in this step at this speed. So you really have like your full kind of detail. And then total number of days, minutes or hours, whatever it is that you want. Usually they count it in number of days rather, but you have to like justify each unit. And then references, of course. That is the main proposal part. So usually for, as I mentioned, that for Japanese facility, JPARC is 4-page limit. So they ask for a lot, but you have to condense into that. So you should focus on the main part. And for ICS facility in UK or Oak Ridge SNS facility in US, their limit is usually 2 pages. But then you have to also provide additional information that if you are really working in this field, so you should have a bit of experience in the field. I mean, not Neutron diffraction, but the field which you are proposing. And then other like just requirement about which kind of temperature you want, which kind of pressure you want, or if you want magnetic field or anything like that. And of course, they also ask you if your material contains some specific kind of elements. These facilities don't allow you to, I mean, that's the norm, not allow you to study any potential and nuclear materials in any way, like which can be used for that. And also some facilities are very like they follow rule that cobalt nickel concentration also should be lower than certain quantity because it can convert to isotope and which can have different kind of uses. Similarly, if your alloy, for example, it has some element, for example, say boron, then it is like above certain amount, then it is really difficult to do neutron diffraction with that because the boron or cadmium, they have very high absorption cross section, so you will not get much out of that. So this is a certain thing that you have to, and also you have to mention like what would be your sample dimension or sample size, and would it be free powder or something like that, because you don't want contamination any sort of there. There are facilities which, I mean, beam lines within facilities which allow biological materials, but still they have their own regulations. So usually in metallurgy industry, you don't have to worry about that, but many things we have to think about. So you have to think about which kind of information you want to obtain, which kind of alloys or materials you are studying, and you cannot really study very small samples at different facilities. Really, I mean, I'm talking about say milligrams or say micron scale. That would be almost impossible. And then your question should be really important. It should have some significance in the scientific community, and you are intending to publish that apply for purposes. Okay, I think today we will stop here, and I think we can have more questions answered if you have any. And as I said, that feel free to contact me. I will be here like okay, I will not come here tomorrow, but feel free to contact me anytime if you want, and if you need any help or information or collaboration. Thank you very much.
Thank you.
Any questions or comments? Right. So the thing which I shown over here, that is just intensity. That is kind of additional part of information which we have. But there are other beam lines which specifically measure texture, kind of like that's the main thing. The main difference comes from kind of physics. For example, you do EBST. First, it's about size, right? Again, like in EBST, you can have limited size, but here you can have more bulk. But that's not the only thing. Second thing is about you can use different kind of environments. For example, magnetic field, for example, temperature, pressure, and so on. So, which you cannot use with EBST. You first have to deform your sample, or you have to apply some kind of thing. But that cannot be really. I mean, when you take it, you prepare sample. And also, sample preparation is a huge thing, and you can introduce different kind of artifacts into that. So, main two factors. One about if you want to look at bulk behavior compared to EBST. Second, you can do in situ. You can apply different kind of environments while you're for example, you're heating, and then you see like how your textures change. Yeah. Any more questions, comments?
I have a question for you. The synchrotron techniques versus synchrotron.
Synchrotron versus neutrons?
Yes, in order to take advantage of
okay. Let me find out. Okay, so everyone knows what is a synchrotron? Yeah. Okay. Say what it is. Yeah. So basically, synchrotron is a kind of X-ray, but we call it high energy X-ray. The X-ray which you use in your lab, X-ray which you do in your labs, that uses some specific target. For example, mostly very common one is copper calcium, which have its wavelength is around 1.5 angstrom. But you can increase it. You are going to go for a different kind of target so that you can cover more like range. So you can maybe use molybdenum or sometimes they have different kind of target. But in synchrotron, you can have high energy, right? So, as you said, it's a large facility similar to actually neutron diffraction. So they also have accelerator, like how for neutron as polishing sources, they also have accelerator. But neutrons are more difficult as they are neutral. They are more difficult to bend and deflect and so on. So in principle, they are similar. The main thing is, and these are high energy X-rays compared to what we have in labs. The main difference is we can have now more penetration data. So basically, the data which you will obtain by a synchrotron, if it is a similar kind of instrument, you are doing, for example, in let me think. Oregon National Lab, for example, in US, they have APS, Advanced Photon Source, where we did some experiments about gain deformation. It follows the same principle, but the main difference is how much we can use smaller samples over there, and its penetration depth is not that much as for neutrons. And as I mentioned, that it depends on materials, which materials are you using. So usually, this is the main difference. How much with lab X-ray we can just go to a few microns, tens of microns, but with synchrotron we can go to hundreds of microns. So it's like one order at least higher penetration depth than lab X-rays. With neutrons, we can, depending on which kind of materials, of course, we have, we can go for some materials up to 10 millimeters or more. But if you have data, you usually deal it in the same way. You can do the same kind of CMWP analysis on data as well, and you will obtain. Basically, we are dealing with diffraction patterns and all information. At least for what I'm talking about here. Of course, if you are doing different kind of Using different techniques, that will be a different story. Is that good enough?
Yes, I was thinking of the time of measurement.
Oh yeah. Okay. This is very important point. Okay, I mentioned a number of times that neutrons are very, very, very slow, but synchrotron is very fast. So usually we get a data pattern from synchrotron that is like after every second you have a new pattern. So you can have really good data quality. So if you want, if for example you have dynamical changes, for example you have phase transformation, or during say heating, it will be very difficult to study with neutrons because you have to hold at that temperature. You cannot do continuous heating, and you cannot have that like a complete picture in neutrons. So that's why I mentioned that. Of course, like I will be talking a lot of like good things about neutrons, but we have to remember everything have some drawbacks. And in this case, neutrons are very, very slow. So the same experiment which may take, I don't know, many hours with neutrons because they're very slow, and you have to come with statistics. I mean, you have to have a statistically good pattern to really do anything about them. With the synchrotron, it's very, very fast. So we measured at APS, and after every 1 second, you have a new pattern, right? And you can really, I mean, especially with these kind of processes where changes are happening very fast, and you cannot hold it at that, say, temperature or pressure or whatever, then I think synchrotron is the best answer for that. So you have to, and for synchrotron, by the way, is also the same method. You have to apply for beam time, and you have to follow the same method and everything. So that's why usually people who work with neutrons, they also work with synchrotron and vice versa. Because both of these kind of facilities, they are government facilities, and you can get beam time, and depending on which kind of problem you are dealing with, so you can decide where you want to go and which kind of experiment you want to do. Yeah, I think that's a very good point. That's very important to remember that there is other players as well in the field, and synchrotron is very good if you have very good changes. Neutrons can be very slow, so that's why it takes way longer time to get a good pattern. And similarly, some materials which you cannot study with neutrons, if they have negative scattering cross section, or if they have high absorption cross section, then again synchrotron could be better answer. So depending on what you want to study and which kind of materials you have, so you can decide. Thank you for the question. Okay. Any other questions or comments? Yes.
SAP is for AP. I'm thinking on chapter 13, stuff like that.
Yeah, I don't. I mean, I don't work with that, but yeah, you can also use neutrons for that. I don't know much about in detail, but of course you can. I mean, I'm aware that people use it for making as well.
Some other question, Spanish or English? ¿Quiere preguntar algo más? ¿En español tampoco? This time I want to ask. How do you select the time? Because I know that you need for my kind of classes to do the emissions. Because this is the, as you say. So how do you select how many parentheses? What do you think to come to selection?
Right. So usually, for example, I can give again about diffraction. So we do tensile loading. Usually in lab we do at 10 raised to minus 3. What is the loading speed? 0.15 millimeter per minute, I think. 1.5 millimeter. So 10 per minus 3 per second. That's the loading speed which we use in labs. But we usually don't do that at neutron facilities. With synchrotron, maybe you can go for higher even. But with neutrons, we usually go for 10 to the minus 5 maybe. Again, depending on sample. But usually we are talking about steel, the most important popular one, or high entropy alloys. So we usually go for 10 to the minus 5. Because if we go with that high speed, we will not have good enough quality if we want to make a lot of patterns. Because we collect data continuously. So we put sample, data collection start. After that, we have to look at data quality. So after that, we decide how many slices. So slices, literally we're making slices, have to cut pattern after like 10 minutes. I don't know, like for each diffraction pattern to have good quality. So then you can have very few patterns. And then maybe you cannot have complete trend. That's sometimes our purpose is to get complete picture. But if you have like missing some places, then that will be, and also that it will average over more like larger area, so it can be like a bit uncertain in that way. So we select depending on where in our material, we know what we want to do. And for example, there can be some material, their deformation behavior can completely change at very slow strain rate. And but we want to look at high strain rate, then of course you cannot use the income. Or you can do another thing. You can do load at some point, 1% say deformation, then like hold over there and then like wait for like some time to accumulate good pattern and then like move to the next one. So it is, we have to know our sample, we have to know our what kind of information we want to obtain from it. So that's how we decide. So as I mentioned about, for example, this steel, we use very slow strain. In elastic, so we also want to know behavior during elastic region, which is very quick. Elastic limit reaches very, very quickly if you use it in very, very slow strain rate. So in that, we usually do like, okay, if the yield strength is say 250 megapascal, so then we can divide that 250 into say maybe 10 steps. So we can go like 25 for each 25 megapascal, we hold it for some time, we obtain a pattern, then we go to the next one, and then so on. So it depends on which kind of information we want to obtain and what is composition also.
Thank you. ¿Alguien más quiere preguntar algo? ¿Español inglés? No? Okay. So, before finishing this course, I would like to give this certificate of appreciation from the head of Departamento of Metalúrgica and Ingeniería to Dr. Naeem for the course and one more for the seminar of okay. So thank you so much for your excellent presentation. Thank you.
Thank you.
So thank you so much for this course. If you want to come to Dr. Naeem, it's all yours. And you can also please go to the coffee break. We have coffee. Thank you.
you.